In this video, I would like to take a look at using complex numbers in operations other than the four basic addition, subtraction, multiplication, and division operations. So what we have here is the addition of two fractions, but of course you see that the denominators happen to be complex numbers. So we can approach this problem in one of two ways. We could take each fraction separately and we could go about rationalizing each denominator, and then we could get common denominators, and then we could go about doing this problem. Or I could get common denominators first and then worry about rationalizing the denominator afterwards. Well, in this particular example, it seems like that's kind of a moot issue because the two denominators happen to be complex conjugates. All right, so instead of going through and rationalizing each denominator first, let's just go ahead outright and get common denominators, because what we'll see is that when we multiply these two denominators together for common denominators, we'll end up with a real number because they're complex conjugates. So I'm going to multiply these two together to get that common denominator. So 5 minus 3i and 5 plus 3i. And of course, on the first fraction, I'll need to multiply by 5 plus 3i over 5 plus 3i to ensure that this fraction gets the common denominator. So 5 times 5 plus 3i plus, and then we have the 3i from this numerator. And the second fraction we'll need to multiply on top and bottom by the 5 minus 3i. Okay, so here's what we have so far. So let's go ahead and do our distribution in our numerator, and then we'll work the multiplication in our denominator and see what we have. So for our numerator, we have 25 plus 15i plus 15i minus 9i squared. And that's all over. And again, since these are complex conjugates, I only need to multiply the firsts and the lasts. So 25 minus 9i squared. Well, okay. The I squared here and here are both just negative ones. So it'll change the subtraction to a positive and the subtraction to a positive there. So in the numerator, 25 plus 9 is 34. And 15i make 30i, all over 25 plus 9, which is that 34. So when I write this sum in standard form a plus bi, I'll have 34 over 34 plus 30 over 34i. Well, that's nice because I can reduce this 34 over 34 to 1. And it looks like both of these I can divide by 2, so 15 over 17i. So for the first example, when we're adding fractions whose denominators are complex numbers, we notice that the denominators happen to be complex conjugates of one another. So just getting common denominators outright gave me a common denominator that was actually a whole number. So when I finished the addition, I was able to write it in a plus bi form, and here's what I get. In this second example, we're going to subtract these two fractions, and of course these two fractions have complex numbers in their denominator. We're actually going to work this second example two separate times. The first time, we're going to go ahead and get common denominators first, and then work it, and at the end, we'll probably end up having to rationalize the denominator. The second time we're going to work this problem, we're going to rationalize the denominators first and then get common denominators and then work our fractions. I would like to just kind of look at this and compare the two methods to see maybe if one is better than the other or if they're both kind of the same. So let's go ahead and get going. Let's get common denominators first, and it looks like between these two complex numbers there are no common factors, so we're just going to multiply them together for our common denominator. So that'll be 2 minus 3i and 4 plus 3i. And so this first numerator was 1 plus 5i, so I need to multiply it by this 4 plus 3i factor that gave me the common denominator here, minus, And then we have the 4 minus 3i that needs to be multiplied by the 2 minus 3i. That gave me the common denominator here. Okay, so when we are at this point, we have a lot of multiplication to do. So a lot of complex numbers that we're going to multiply together. So a lot of distribution, a lot of like terms. So 1 and 4 makes 4 when I multiply, plus 3i, plus 20i, and then plus 15i squared. So this minus sign right here, I'm just going to leave, and then I'm going to put this next multiplication in parentheses, because then I'll have to distribute the negative, and I don't want to get the signs of these terms wrong. So I'm going to be very careful. 4 times 2 is 8, and minus 12i minus 6i plus 9i squared. And that's all over the denominator being multiplied through. So 8 plus 6i minus 12i minus 9i squared when I multiply those complex numbers. So let's go ahead now and distribute the negative through. So 4 plus 3i plus 20i plus 15i squared minus 8 plus 12i plus 6i minus 9i squared. And then in the denominator, let's go ahead and work with this. So I squared is negative 1. So the negative 1 will change this negative to a positive. 8 plus 9 will be the 17. And then 6i minus 12i will be a minus 6i. So in our numerator now, let's go ahead and put all this stuff together. So our I squared is a negative 1. So it'll change this positive 15 to a negative 15. Similarly, this I squared, which is negative 1, will change this negative to a positive. So let's go ahead and combine our real parts. 4 minus 15 is negative 11, minus 8 is negative 19, plus 9 is negative 10. And 3i and 20i make 23i, plus 12i is 35i, and 6 more makes 41i, all over 17 minus 6i. Alright, so as promised, we have common denominators, but we have to rationalize this denominator because we have this I in the denominator, which remember is the square root of negative 1. Can't have a radical in the denominator. So we're going to multiply the top and bottom by the complex conjugate. So I'm going to multiply by 17 plus 6i in both cases. So again, more multiplication. Alright, so I'm going to kind of scoot over a little, make some room. So the negative 10 times 17 is negative 170. Negative 10 times 6i is minus 60i. 41i times 17 will be a plus 697i. Let's see if we have room here. And then 41i times 6i will be a plus 246i squared. Okay, so that's what that looks like. I'll venture back over here. And then let's multiply these complex conjugates. So 17 squared is 289. And then negative 6i and positive 6i is negative 36i squared. Okay, so here we are. A couple of I squareds. So this one will make this negative. This one will make this positive. So negative 170 minus 246 should give us something like negative 416. And then negative 60i and positive 697i should be something like plus 637i. And then, of course, 289 plus 36 will be 325. To go ahead and get this in standard form, though, I need to write it as a plus bi. So it'll be negative 416 over 325 plus 637 over 325i. It looks like, yeah, I can take a 13 out of everything, actually. So divided by 13, divided by 13, divided by 13, divided by 13. So each of these fractions will simplify. When I do that, it looks like negative 32 over 25 plus, let's see, 49 over 25i. Alrighty, so the way we tackled this subtraction problem was we noticed they had complex numbers in the denominators. So we got common denominators first, and then we went ahead and rationalized this denominator, and this is our answer. So here in a second, we're going to rework this problem, and we're going to do it the other way. We're going to rationalize the denominators first and then get common denominators. So let me get a fresh piece of paper. Okay, here we go again. Fresh piece of paper and problem reset. Let's do this thing. So instead of getting common denominators first, we're going to go ahead and rationalize each denominator first and then worry about common denominators. So on the first fraction, we have 2 minus 3i in the denominator, so we need to multiply both the numerator and denominator by the complex conjugate, which is 2 plus 3i. So I'll put parentheses around all that. Similarly, with the second fraction, the denominator is 4 plus 3i, so we'll multiply the numerator and denominator by the complex conjugate, which I'll just change the sign, so 4 minus 3i. And it happens to be an interesting relationship because the top is going to be squared and the bottom is going to be complex conjugates. Okay, so when we multiply through the first, we're going to distribute here and here, and then the denominators are just firsts and lasts. So we have 2 plus 10i plus 3i plus 15i squared all over, and it looks like 4 minus 9i squared. And we're going to subtract from that, this distribution, 16 minus 12i plus 9i squared. And then, of course, the denominator is 16 minus 9i squared. Well, alrighty. All of our I squareds are actually negative ones, so I'm going to go ahead and cross all of them out and change the sign in front of each one of them. Alright, so now let's combine like terms. 2 minus 15 is negative 13, and 10i and 3i is 13i. And the denominator there is actually 13 as well, so a lot of 13s. Over here on the right side, we're going to have 16 minus 9, which is 7, and then minus 24i all over 25. And this is a subtraction problem, so let's not forget that rascal. Let's go ahead and write all of these things in a plus bi form first, so we can simplify a lot of stuff here. So this will end up being negative 13 over 13 plus 13 over 13i minus 7 over 25. And then since we're subtracting this fraction, this minus and this minus will end up being a plus sign. So that's where we are. And of course, nice things happen because this will become negative 1 plus I minus 7/25 and then plus 24/25 I. Well, okay, so if we have negative 1 and then a negative 7 over 25, they have the same signs, so it'll be negative. And getting common denominators will turn this into negative 25 over 25. So the whole thing then becomes negative 32 over 25. Similarly, we're adding 1i to the 24/25 I. So when I get common denominators, this turns into 25 over 25. So it'll be plus 49 over 25i. And that's as simplified as we can make it. So there's the final answer, and you can look back and you'll see that it's the exact same answer we had previously. Of course, it should be, since we're just still subtracting the same two fractions. But we just went ahead about the problem differently. So the first time we went through and we found common denominators first and then rationalized the denominator. In the second method, we rationalized the denominator first and then found common denominators and combined the real parts and imaginary parts. So same answer. So what do you think as far as which one was easier? I think maybe the first one took a little more time explaining and working through. And the second one worked out pretty nicely because of all the simplification here, but it was likely that it only occurred that way because of this particular problem. So it's probably 6 one way, half a dozen another as far as how you go about tackling problems of this nature.